Let's look at Chief Mate's MCA Stability Examination, November 2013, question number 1. It says, a box-shaped vessel floating at an even keel in salt water has the following particulars. Length 112 meters, breadth 24 meters, depth 10.120 meters, draft 6.2 meters, kg 9.64 meters. A midship watertight compartment 19 meters long, permeability 0.80 and extending full breadth of vessel is bilged. Calculate each of the following. A. The final draft. B. The metacentric height in the flooded condition. C. The righting moment at the angle of deck edge immersion in the bilged condition. We'll first make the drawing. So this is the box-shaped vessel. The length of the vessel was given as 112 meters. So this is the length of the vessel. The breadth of the vessel was given as 24 meters. So this is the breadth of the vessel. The depth of the vessel was given as 10.12 meters. So this is the depth of the vessel. The length of the flooded compartment was given as 19 meters. So this is the length of the flooded compartment. And the permeability in the flooded compartment was given as 0.80. So this entire compartment, which has been filled with yellow color, is the compartment which has been bilged and it has permeability inside. The draft of the vessel was given as 6.2 meters. So we will first calculate part A of the question, which asks us to find the final draft. So we'll use the formula buoyancy lost is equals to buoyancy gain. The buoyancy lost is the length of the compartment, which is the small l, the breadth of the vessel, which is capital B, the draft of the vessel, which is 6.2 meters, times the permeability. So this is the buoyancy lost. So this was the length of the vessel, this was the breadth, and this was the draft. So this entire region is termed as buoyancy lost. But since it has cargo inside it, gives us the permeability, and due to this, there is not 100% loss in the buoyancy. So we will multiply the loss of buoyancy with the permeable factor, which was given in the question as 0.80. So buoyancy gain would be now this entire length minus the permeable length, because this is not the total loss in length, because we have still cargo inside it. So we have a partial loss in length. So we have to apply the correction for the partial loss. So the partial loss in the length of the compartment is the length of the compartment multiplied by the permeability. So this will give us the loss of length. So the buoyancy gain will take place over the total length of the vessel minus the permeable length, which will be the length of the compartment multiplied by the permeability. So we have written it like this, which is the length of the vessel minus the permeable length. So buoyancy gain would be equals to the length which is taken into consideration after the vessel has been built and permeability is considered. So this is the length of the vessel, this is the breadth of the vessel, and multiplied by the sinkage. When we fill in the values, the length of the compartment was 19 meters, which was filled here. The breadth of the vessel was 24 meters, which has been filled here. The draft of the vessel was 6.2 meters, which has been filled here. The permeability of the vessel of the compartment is 0.80, which comes here. When we fill on the values in this equation, the length of the vessel was 112 meters. The small l is the length of the compartment, which was 19 meters, times the permeability, because there is not 100% loss in the length due to the presence of cargo. So permeability is 0.80, which was given in the question. times the breadth, which is 24 meters, which comes from here, times the sinkage. This is what we need to find out. When we solve this equation further, this entire value will give us 2261.76, which will be equals to 112, which is this number as it is, minus the product of these two numbers. So product of these two numbers is 15.2. Again, the brackets times the 24, which is as it is here, times the sinkage, which is as it is here. Solving on this equation further, we'll get 2261.76 is equals to 96.8, which is when we subtract 15.2 from 112. So this is 96.8 times the 24 times the sinkage. So times 24 times sinkage. So with this, we will be able to find out our final sinkage, which was found out to be 0.974 meters. Now the final draft will be equals to the initial draft plus sinkage. So final draft is equals to 6.200 meters, which was our initial draft, plus the sinkage, which was 0.974 meters, which has come from here. So final draft is equals to 7.174 meters. So this is the answer to part A of the question. The part B of the question asks us to calculate the metacentric height in the flooded condition. So for this, we first need to calculate our Km. So Km is equals to Kb plus Bm. If this is the bilged condition, then Km bilged will be equals to Kb bilged plus Bm bilged. So this is how we'll be calculating our Km. So Kb bilged is equals to draft bilged divided by 2. So draft bilged was 7.174 meters divided by 2. So this was the draft bilged. So we have given the input as draft bilged as 7.174. So we have found out Kb bilged as 3.587 meters. Now Bm bilged. So Bm bilged is equals to length effective multiplied by breadth cube divided by 12V. This length effective, it has been inked in blue so as we give the most attention to this part. So this length effective is basically the total length of the vessel minus the product of the permeability and the length of the compartment. If we observe this value is actually same as what we had used while calculating buoyancy gain. This value and this value. So the principle remains same, which has been explained earlier, multiplied by the breadth cube, which is 24 cube, divided by 12V. So 12 times length, which is 112 meters, times breadth, which is 24, times the draft, which is 6.2. When we solve it, we'll get the final answer for Bm bilged as 6.691 meters. Now Km bilged is equals to Kb bilged plus Bm bilged, which was explained earlier. So we'll be able to find out our Km bilged. So when we interchange the values for Kb bilged and Bm bilged, we'll get 3.587 meters, which has been obtained from here, plus Bm bilged, which is equal to 6.691 meters, which has obtained from this place. So Km bilged is equals to 10.278 meters. Once we know our Km and we subtract the Kg of the vessel, we'll get Gm of the vessel. If the Km is in bilged condition, then Gm what we'll get will be in bilged condition, because in the entire bilging question, we assume the Kg to be constant. So Gm bilged is equals to Km bilged minus Kg. Gm bilged is equals to 10.278 meters, which is the Km bilged of the vessel, which has been obtained from here, minus Kg, which is 9.64 meters, which was given in the question. So Gm bilged is 0.638 meters, and this is the answer for part B of the question. Now let's look at part C of the vessel, which asks us to calculate the righting moments at the angle of deck edge immersion in the bilge condition. For this, we'll make another drawing, which is the transverse section of this box-shaped vessel. This was our initial draft. Now, since the vessel has been bilged already, this will be the bilged draft. In order for this vessel to come up at an angle of deck edge immersion, let's say on the starboard side, the final water line which has to be observed would be this, which passes through the angle of deck edge immersion once the vessel is listed or heeled. Our initial water line, which was the bilge draft, was this value. So the list or the heel which is supposed to take place to bring the vessel at angle of deck edge immersion would be this angle. Now, when we look at the triangle A, B, and C, which is right angled at B, we can say that AB is nothing but the bilged freeboard, because from here till the bottom is the bilged draft, from here till the end is the depth of the vessel. So if we subtract the draft of the vessel from the depth of the vessel, we will get the freeboard. So we can say that AB is equals to the bilged freeboard. Now this entire thing was the beam of the vessel, and this is the center line which is passing through the center. So BC is exactly the half of the beam of the vessel, because this was the entire beam and this was the center line. So BC would be exactly half the beam of the vessel. So we can say that in triangle ABC, which is right angled at B, this is triangle ABC, which is right angled at B, we can say tan of theta deck edge immersion is equals to perpendicular divided by the base. So this is the simple trigonometric formula which says the perpendicular, which is AB in this case, divided by base, which is the BC in this case. So we have put perpendicular as AB and we have put base as BC. So perpendicular is nothing but the bilged freeboard. So we can write it as the depth of the vessel, which was 10.12 meters, minus the bilged draft. So this was depth of the vessel and this was the bilged draft. So if we take off bilged draft from the depth of the vessel, what we'll get is the bilged freeboard. Same way we have done it here, which is 10.12 meters is the depth of the vessel and 7.174 is the bilged draft. And when we take off 7.174 from 10.12, we'll get the bilged freeboard. Divided by BC. So BC is 12 meters because the entire beam or the entire breadth of the vessel was given as 24 meters. So BC is equals to half the beam. So BC is equals to half times 24, which will give us equals to 12 meters. So that's why we have put it as 12 meters. When we solve this further, we'll find tan of theta deck edge immersion is equals to 0.24550. Theta deck edge immersion is equals to tan inverse of 0.24550. And we found out theta deck edge immersion to be 13.8 degrees. So this angle was found out to be 13.8 degrees. Now we know that our theta deck edge immersion is 13.8 degrees. So we can calculate the GZ value for that angle of heel. We'll use the wall-sided formula, which is GZ equals to GM bilged plus half PM bilged multiplied by tan squared theta times sine theta. We won't be using GZ equals to GM sine theta because this is only valid for small angles of heel. Small angle of heel. So we cannot use this formula, which is GZ is equals to GM sine theta. And we also cannot use GZ equals to Kn minus Kg sine theta, because we don't know the Kn value. So these two formulas have been eliminated. The only thing what we have been left is the wall-sided formula. And also the wall-sided formula is applicable up to deck edge immersion only. So that's why we have used the wall-sided formula, which is Gz is equals to Gm bilged plus half times Bm bilged times tan square theta multiplied by sine theta. We have to be very careful about the brackets which have been used here. So Gm bilged was found out to be 0.638 meters, which was earlier in part B, which is this. And Bm bilged was found out to be 6.691 meters, which has also been found previously, which is here. And tan square of 13.8 degrees. So theta is basically the angle of heel, which we had found out to be 13.8 degrees at deck edge immersion. And sine of theta is again sine of angle of deck edge immersion, which is sine of 13.8 degrees. When we solve the values inside this brackets, everything will get 0.83984 multiplied by sine of 13. When we solve it further, we'll get Gz is equals to 0.200 meters. Now we had been asked to calculate the writing moments, and we know that writing moment is equals to Gz times the displacement. Now we know Gz, all we need to do is multiply it with the displacement and we'll get the writing moments. So writing moment is equals to Gz times the displacement of the vessel. So writing moment is equal to Gz, which is 0.200 meters, which has been obtained from this place, times the displacement of the vessel. So displacement of the vessel can be written as the length of the vessel times the breadth of the vessel times the draft of the vessel times the density in which it is floating. Now it's of most importance that we use the initial draft here. We cannot use the bilged draft here, because the assumption for solving the bilged quotient by lost buoyancy method is number 1, that underwater volume constant, number 2, displacement constant, and number 3 is kg constant. So the displacement is constant. That's why we'll be using the initial displacement, which is the length of the vessel, the breadth of the vessel times the initial draft times the relative density. When we put in the values, we'll get 0.200 multiplied by the length of the vessel, which is 112 meters, times the breadth of the vessel, which is 24 meters, times 6.2 meters, which is the initial draft of the vessel, times the relative density in which it is floating. So the vessel is floating in salt water, so relative density is 1.025. When we product all these numbers together, we'll find out the writing moments as 3416.4 tons meter. So this is the final answer for part C of the question.